Okay, so we can start with the introduction. Hi, everyone. My name is Noah. I'm a co-chair of Pydata Berlin, and we have here also Theo and Valentina from the Pydata Berlin team. As far as I can see, maybe some others.
Daniel, I guess.
Who?
Daniel?
Daniel? Hi, Daniel. Yes, we are Pydata Berlin. We are Yes, we are the Berlin chapter of Pydata, and Pydata, as some of you may have heard before, is the educational program of NumFOCUS, and we will talk about it will be introduced very soon. Our program for today is me. I am your introduction happening now, and then we have two very cool talks. One is from Kattia Flores Pozo, who will talk about controlling many satellites at the same time. And then we will have the second talk from Niladri Shekhardut about deepfake and why he has trust issues. Let's hope he can solve them. Some of them today. In between, we will have a 5-minute break, and at the end, we can all meet up in this nice platform called Wonder. It's kind of a spatial chat thingy similar to Gather Town, where you can walk on your screen and talk in smaller groups and chat. And later we will post in the chat the link so we can all gather there later. This meetup is recorded, so both talks are recorded and are also streamed now in YouTube, so please take it into consideration. For both talks, if you have any questions, please write them down in the chat and we will pass them on for the speaker at the end of their talk. Also, if you're watching on YouTube, you can also write down the questions in the YouTube chat and we will pass them on to the speaker. So yeah, as I mentioned, we are Pydata Berlin. We are the local chapter of Pydata, which is kind of a worldwide thing. We started in 2016 and we had quite a lot of fun meetups and conferences ever since. We are a monthly meetup every third Wednesday of the month. You probably found us on meetup.org and you can just register and come to all of our meetups. Sometimes these questions comes up. We are all volunteers here, so doing it, not clear why, but yeah, no one pays for that. We have a code of conduct, which is the NumFOCUS code of conduct. In short, be kind to each other, and please remember that the code of conduct applies also when we are online. And if you are in Berlin and you are interested in Python and you would like to contact and get in touch with other people who are interested in Python, you're welcome to join the Python Berlin Slack. There's also a data science channel that you can follow, and also sometimes there are job posts there, or you can ask technical problems. So we're gonna start now with the first talk. This is us, Pydata Berlin. You can follow us on Twitter, and this is our website. I will stop the share now. It is sharing the screen, and I think Valentina will introduce our first speaker.
Yeah, hi everyone. I'm Valentina, also co-organizer of Pydata. I have the pleasure to introduce my colleague, Kattia, who will be speaking about how Planet operates more than 100 satellites using agile aerospace. Katja is the lead of the space operations team for Planet, and she has a background in telecommunication engineering, but also a passion for space. And she has been working in the space operations for the last 7 years. So she's been scaling operations from starting from 5 satellites to more than 300 satellites launched to date. So, Katja, welcome.
Thanks, Valentina, and thanks to Pydata for having me. So let me share my screen. All right. Yeah, so I'm going to talk today through what does it mean to operate satellites, and then what does it mean to operate hundreds of them. So yeah, as Valentina mentioned, I'm the team lead of the space operations group at Planet. So we are actually a small team of people, less than 10. And I want to start with showing you what does the constellation that we operate look like. I think a visual way is the best way to do it. Thanks. Right. So this is a day in the life of a dove. So we call our satellites doves because they remind us to that they have 2 wings. So yeah, we call them doves. And then a group of satellites, we will call them flocks. So basically what our sats are doing, they are taking, they are Earth sensing, air remote sensing satellites. So they are taking pictures of our Earth continuously, exactly as the simulation shows. So they are acting like a line scanner. So it's like having multiple cameras on the same plane, different planes, just doing that, taking images of landmass as they pass over the Earth. And having that constellation on the space allows us to take daily images of the entire landmass of the Earth. And by having all that data, then we are able to inform decision makers and provide that visibility on changes that happen on the day-to-day that weren't there available before. All right, so I want to give you a quick overview to what a constellation of satellites look like. So we had actually 3 types of satellites. So when I started working on space operations, I was working with the Rapid Eye constellation. So those are 5 satellites, the size of a fridge. And they were launched in 2008, and they have been taking images up to 2020, so last year. So we have this huge archive of data for all these years from this constellation. And of course, even though they were designed to last 6 to 7 years, they outgrow that period of time. So they continue taking images even years after, but it reaches a point where you know there's such degradation that we wanted to make sure that we had the capability of lowering their orbit so that they could be safely re-enter the atmosphere within a time that is responsible. And then we have the doves and super doves. So we have 2 generations of satellites, and that's why we call them super doves. Super doves are the latest iteration of our sats. So we have launched to date more than 300 of these, and we currently have in orbit more than 180 of these sats. So to give you a sense of the scale, how different these sats are to the Rapid Eye. So the Rapid Eye are like a mini fridge, and the doves are like a shoebox size. So 30 by 10 centimeters, they're very small, but they have very similar capabilities. So they take images, what we call medium resolution. So that means a pixel is equivalent to 3 meters, something that will be 3 meters on ground. And then they image the Earth on different bands. So there are the visual bands that we see, red, green, blue, and then additional bands that will help us identify things like vegetation, vegetation indices that will help for agriculture detection, for example. And then we have a constellation of high resolution satellites. These are, we currently have 21 in space, and these are about the same size as the Rapid Eye, so also like a mini fridge. But these sats have the capability of taking like really high resolution images, so sub-meter resolution. Okay, so that's what we have on space. So it's like having all these cameras around, like orbiting the Earth. So what system do we need to actually talk to the satellite and then make sure that we are getting health data from them and that we are getting all those pictures that they are taking down? So this is in a nutshell what our system looks like. So there's the space segment, so which is all this group of satellites. And then we, of course, have radios on board of them so that we can talk to to ground stations on Earth. And because we have such a large number of satellites on space, we also need a large number of ground stations on the ground. So operations is not only about taking care of the satellites that are on space, but also taking care of the systems on ground that support the space system. So I'm not gonna go into the detail on the radio frequencies and all, but there are like, to simplify, there are two types of communication. So a low speed one and a high speed one. So with low speed communication, we can get health data from the satellites and upload commands to them. And with high rate radios, then we download, all the images, which are a larger amount of data. And then we need systems that will orchestrate how each of these resources are used, like to which satellites each antenna talking, how many times a day, what is each satellite doing on a given day, like where is it taking images, when it's supposed to point to the ground station to download data, when it's supposed to point to the ground and actually take a picture. So those systems are also built in-house for us. So there is a scheduler that will make sure to deconflict those resources. There is mission control. You probably have in mind the picture, like in the latest Mars rover landing, you see like a lot of monitors, each of them monitoring a subsystem, and then engineers behind them, sending the commands and monitoring the telemetry that comes from the spacecraft. So basically that's what mission control does, but in a different setup. So mission control for us is built on the cloud. So, and it doesn't have a lot of people sitting 24/7 in front of them to monitor the sats. So that is possible because we have a lot of automation in place, and I'm gonna elaborate more on that later. But just to have the two differences. So mission control for me is like, now I'm sitting at home in Berlin and I can access it through my laptop, or like from my couch, and then I can command the satellites from there. And then of course we need like a place where we store all the data that comes down. So we have logs, we have telemetry, we have pictures, and we want to make sure that all these systems are built such that we can build on top of them, so that they all have endpoints, that we can query that data with other scripts that will run on top. So those were designed from the very beginning with that on mind. Yeah, and then we have a different, what we call pipeline for the images. That's a different storage where each of the pictures get processed, and there's some quality checks in between. All of that automated, because daily we download more than 15 terabytes of data. So we have to process all that data, of course, in a very automated way. Yeah, and then once the images go through all that processing pipeline and image quality checks, then they get published and delivered on a platform that our customers can access. Cool. So how we do all of that? Of course, this wasn't like the picture at the beginning. So we use agile aerospace on everything, but what does agile aerospace mean? So it's on its core is rapid iteration. So on everything. So from manufacturing the satellites to iterating quickly on the software the satellites are running, on the software that we are running on ground, on how we do testing. So one good example of rapid iteration is these doves. It was actually not just one model. So we have had more than 13 iterations over time. Now we are past 13. So what we do is put some new components, put the new software, launch a new tech demo, test it on orbit, and if that works, then that will become the next version to launch. So that's how we have been able to progress very quickly and get like always the latest and best packed into this 3-unit CubeSat form over the years. And that also happens on the software side. So the way we process the data from a space operations point of view to now has changed following that agile aerospace mentality. And a key part of this when trying to do this is also always building the tools with that on mind. with having a scalability on mind, knowing that, okay, now we are operating 20 sats, but in a year we might have 200 on orbit. So that makes things easier and makes the system just robust to handle what comes on the roadmap. And I want to make a pause on talking about agile to get into something exciting, which is this is also agile. So to have that large number of satellites in the space, you need to launch them, and launchers are also well, now the market is growing, but it's something that constrains, right? There are only enough launchers in the world, so we need to make sure that we are launching as often as we need. So this is just a snapshot of what the year looked like for us, like the last year. So we had launches with 3 different rockets. Oh, sorry. Okay, thanks. Yeah, so we launched from a European rocket, the Vega. There we had 26 of our newest doves, which we call super doves. And then something interesting of that rocket is we had 2 different deployers. So the satellites get deployed from what we call quad pods. So it's basically like boxes with a spring that release the sats. But there were 2 different of those systems on board. So that was something new for us. And then we launched 6 of our high resolution SkySats with SpaceX. We actually had 2 SpaceX launches, 1 Electron, 1 Vega, actually 2 Electrons. So just that's another part that is also agile, using as many opportunities as we can to get sats into space. And to give you an idea of the amount of data that we have to deal with, the global ground station network last year collected over 5 petabytes of data. And our most recent launch was actually on January. I put this because this was very exciting. So it was a record-breaking launcher. You probably have seen, I don't know if, well, I always see the live transmissions for any rocket launch, but this was a SpaceX record-breaking one because this was the most small sats ever launched all together. So 143 satellites were put all together on this rocket, and they all had the same ride. So here we launched 48 super doves. So also on two different deployers. And this was our 30th successful launch so far. This is one of the images that one of our sats that were launched on that rocket took right after being commissioned. Cool. Now I'm going to talk about how they operate, so the concept of operations, so that you have an idea of what we have to do as a space operations then for automation. So our doves are a monitoring mission. So monitoring means they are always taking pictures over landmass, because that's our point of interest. And then, like, if they are not taking images, then they are talking to the ground stations and downloading that data. And when they are not doing either of those 2 things, to be able to have them as a line scanner separated like in the video, we need to phase them out. So space them out along the orbital plane. And to do that, we use differential drag maneuvers. So like the satellite will be rotating so that the atmospheric drag will affect its position in relation to the others, and they will slowly separate among the plane. So those 3 things, so it's pretty simple. Well, it sounds simple, but yeah, that's basically what the sats have to do. And one important thing to mention is, like, we don't do 24/7 ops, so there's not a person there looking what each satellite is doing all the time, and that's because we have a lot of automation in place. So what we call nominal operations is basically all the tasks to make sure that the satellite is healthy and it's doing what it's supposed to do. So for us, that, it's able to take pictures, and it's taking pictures, and it's able to download them to the ground stations, and it's downloading them. So the first thing of all is, like, how do you tell the satellite what to do? So there comes the scheduler. So the scheduler is an optimizer building house that will every day, score areas of the landmass that each of the satellite can better take a picture of, and then, like, that combined with the power budget of the satellite will just distribute imaging activities, we call them, so slots where the sats are taking images to each of them and to the whole constellation. And then based on like how many pictures the satellite has taken, so it has a lot of other parameters, and then it optimized for how to better distribute all the available time that the ground stations have. So the scheduler will take care of doing that autonomously. It runs daily, many times a day. So that's one thing. So we don't need an operator or a person like deconflicting or creating schedules for the satellites. Yeah, so that's very important. Also important not only for the space segment, but also for the ground network. So we have more than 40 antennas distributed across the world. So it will be just unsustainable to have, persons dedicated on each of in each of the locations, and also they have to act as a network. Right? And then we need to know how each of the satellites are doing. So once they are talking to the ground station, that data will come down. And instead of looking at each of that data, and just to give you an idea, our ground stations run more than 2,000 passes a day. So yeah, it needs to be automated. And also the way the images are processed. So yeah, so let me talk about what are our tasks, so I can go more into detail on the automations. So what's a space operation? So from the moment the satellites are manufactured on ground, and then they're put on a rocket, and then they are launched. So as soon as they leave the deployer of the rocket and they are in space, that's where our task starts. So we, as a space ops, are responsible of the commissioning of those sats. Commissioning means making sure that all the subsystems are working as expected, detumbling the satellite. So when they are deployed, they are tumbling at a given rate. So we want to make sure that we have the attitude controlled, that we check that the radio is working, that the camera is working. So all of that process needs to be done for each of these satellites, and as soon as we can. Right? So for that, we have also built in automations. And actually, this last launch was one of our best commissioning process. So something that would take in the past more than a week to do. So commissioning would last like per satellite about 7 to 10 days. We managed to achieve that, to reduce that to less than 2 days. And that's because we built in automation on board and also on ground. So once the satellites are commissioned and they are starting to do what they have to do, taking pictures and downloading, we move into a monitoring stage. So we have to monitor that not unexpected things are happening, that anomalies are being resolved or are being caught. And then at the same time, as part of our agile aerospace, we will continuously test things on orbit. So call them experiments or testings. So obviously we have testing on ground. So we have satellites on ground where we test things first, but we also test things on space. So we have, we call them canaries. So they're like or staging sats, the sats where we will test something first to make sure that everything's fine, and then roll to the whole fleet. And then anomaly debugging, of course. So when something comes up and we need to fix it, we need to look into it. But we are also working towards making this more autonomously. Then yeah, software, we continuously update the software that is running on board the satellite. So that's a big part of testing on ground and also testing on orbit. And then when the satellites reach their end of life, then there is a retirement process. But it doesn't end there. So once the satellite is no longer productive and we have had to retire it, there's a lot of data from that satellite, so from their whole lifetime. And that data will help us create models, degradation models or forecast models, what to expect from next generation satellites. All right, so moving into how space operations change with the amount of satellites. So obviously some years ago, we had a tenth, even probably a bit less now, of the amounts of satellites that we have now. Although mission control was built in for scalability, there have been already many iterations. So, but the principal feature was that we wanted to have a mission control that will be able to talk to the ground stations and handle the communication with the satellites on its own. So that was a key stepping stone. And then the first satellites that we launched were a way for us as a space operations to learn, like what data we should be looking at. So basically gather operational experience. So initially, what our job looked like was going through reports, so logs that capture things that were happening on ground or things that were happening on board the satellite. And then we'll have some sort of scripting that will filter or group things like similar warnings or similar captures. And then we'll have that summary per satellite. And then an operator, one of us, will have to look into each of those alerts and then understand the root cause and then come up with a mitigation. So we will look at that daily per sat, but of course, as the number of sats increased, that became unsustainable. Yeah, it was time consuming. You need to evaluate every alert. And as we were constantly iterating, there were new things or new features on the satellite. So there were different performance value across satellites. And of course, as the number increased, there was more data to parse through. So I remember there were days where like it took us half a working day to go through all of the alerts. And now it takes us less than an hour. So what changed? So we had to move from the traditional space operations mentality of let's look at what happens with each individual sat to what do we expect from the whole fleet. So we shift that on our minds and say, okay, let's first look at the value of the constellation. So what is important is that as a whole, as a group, these satellites have to deliver this amount of data and they have to download it within this time. So what we look at now is we build metrics with scripts that will aggregate that data for us, and that will be the first indicator if the fleet as a whole is operating as it should. And then if not, then we know there is a fleet-wide issue, and then we have built alerting systems for those metrics that matter the most to us. And we will only react to those alerts then. And then the second layer is identifying the doves or the sats on the fleet that have some non-nominal behavior. But we don't want to do that by looking at each of them. So what we want is for the metrics to tell us, we expect this performance from this sat, but there has been this deviation, and then we just want to see the alert. And we want to see the alert on the specific thing that we have to look at. So that's what we have now. And then the next step is like, okay, now we know this alert on this specific issue has popped up. How do we mitigate this? So once we have the mitigation path, we want that the next time this happens, that we have a script on top. We have a script that detects the issue, and then we have a script that just applies the resolution automatically, so without us knowing. But of course, we want to have visibility on how many times this happens. So we make sure to build metrics around everything, our automations, and the performance. So by doing this, we optimize the system availability and the capacity, because there is less engineering time spent at looking at individual things. Investing in automation frees up a lot of our time on that, and then makes the responses way quicker. And so rather than a person looking through something and then there's some delay time between like, okay, coming up with the response and applying the response, the automation is just taking care of that immediately. So that has been a great positive change. So yeah, I talk a lot about metrics. So I mean, this is a very simple diagram of what we have in place as a space operations, but it's basically that. So we have the different entities of the system. So we have mission control that has data from each of the satellites and each of the ground stations. We have orbit data from the sats, we have telemetry, we have logs. All of this data is stored in such a way that we can, that we have endpoints to query that data from. So it's easy for us to build scripts on top. We use Python for this. We have a lot of scripts that, like a group of them that we call mission metrics, that will tell us everything from the high level performance of the fleet to like specific performance data per satellite and per subsystem. So it just gives us the granularity that we need, and also it abstracts to true high level metrics. And then we can decide how to use this data. That's the great thing. So we can, from there, use those aggregated records and then build automated responses on top, do analysis on Python notebooks, or simply like display the data on visual ways, like using tools like Grafana or Kibana. So it's just like a very powerful way of using data analysis on any issue that can come up. Yeah, so over the years, and I would say especially the last 2 years or so, yeah, the role of the space ops operator has been taken over by the automation. So well, we call it Autobot, but it's not. That's why the logo here. But the automation has taken that role. So it takes care of the common anomalies and maximizes the performance of the fleet. Cool. This is a specific example of one of the automations. This might be going into too much detail, and actually one of my colleagues talked about this specific use case on Pydata about more than a year ago now. So maybe it's time for us to do another deep dive on this. But this is just one clear example of where automation is just very important. So we use a job that sets the duty cycle on each satellite. So the duty cycle is how many times in a day the satellite will spend imaging the Earth. So it only can do so much because there's only so much land to take pictures of, and also because there's only so much power. So the power depends, because we have solar panels, the power depends on the sun beta angle. So across the stations in a year, that angle changes. So we want to make sure that our power models and the duty cycle includes that change. So the lower the beta angle, the lower illumination the panels have. So the lower the power it's available to the satellite. So we want to make sure that we know that, and the satellite knows that, so that it's not overdoing itself, like it's not trying to take more pictures with the power that it doesn't have. So this is obviously, it will make sense to do this manually and like checking every time of the year when we have to change this. So basically that's what an automation is doing, is just checking the power telemetry, saying, okay, the voltages on board look okay. If there is a dip and a flag has triggered on the power system, then it will say, oh, you're doing much more than what you need to do. So let's reduce your duty cycle. So it's doing that tuning for us. And by doing that, we are keeping the satellite healthy, and we are also making sure that when we have a lot of power, we are imaging as much as we can, and when not, we are dialing it back. Cool. So yeah, that's just one example of the many things that we have to control, but that are just made easy by having ready available metrics that we can aggregate in any way we can. Yeah, and then build on top of that. So what's next? So we have reached that point where we feel comfortable with, like the detection and mitigation and the metrics that we have. And now we are trying to explore with machine learning applications. So we have all this data already aggregated in many ways. So what we are trying to discover is how we can make use of that historical data altogether. So what we have in mind, like maybe in the long term, it's being able to predict the anomalies. So we know some signatures, we have the data of all the subsystems. We also have operator data when an anomaly has happened. Like as an operator, as a human, what are the things you have to look at? So training those data sets with that might help us be more predictive and also predict performance degradation. So we know, okay, we have a better model for forecasting. And eventually, just having an autonomous fleet that requires no human in the loop. That's like the ultimate goal, but yeah, we're not there yet, but those are some next steps. Cool. And I wanted to end, because I talk a lot about space and launches, but why is this important? So abstracting a bit from the technical side of things, and actually these are some applications that, you know, where Python or any type of data analysis is super powerful. It's to play, not to play, but to actually use the data that comes down from the satellites. So to me, this is a very, oops, sorry. This is a very powerful video that just shows what can be observed. So this is data from, this is an image from the Amazon forest from 2017 till last year. So, because we have daily images, you can see how things change across time. Yeah, so it's just, I think it's just powerful, and it's something that adds this visibility that we didn't have before. Yeah, you can see the forestation, how it's increasing across the days. Yeah, I mean, it's very sad, but yeah, this is a really good example of the impact that our data can make and of the applications of Earth observation imagery in general. Cool, thanks. Of course, there's some time for questions. I think I might have extended myself a bit, but if you're excited about what we do about space, anything space operations, data analytics, you know, we are hiring a lot, so check out our career pages or let me know if you want to know more. Thanks. So.
Thanks a lot, Kattia. Was very interesting. I mean, I'm biased, but okay. Would you, Theo or Noah, help me with the questions? We have questions both in YouTube and I guess here.
Please write your question in the chat if you have any. We have a question from YouTube, which what is the lifespan of these satellites from launch to their retirement?
Yeah, so the design life is up to 3 years, but we have definitely seen sats that have lived more than that.
Thanks.
I see a question. Are the images available to the public?
There are 2 different programs. So just recently we signed an agreement with the Norway government. It's called NumFOCUS. So that's opening data for forests around the world. So there are different ways where the data can be shared. I encourage you to visit our website for more info.
Another one.
Here. Yes.
Yeah.
Go on.
Assuming this is open data, are you tracking who is using these images? It will be nice to see the applications.
Well, we definitely have a research program where universities do different studies and like applications with our data, and those are available through paper and scientific publications. I'm not sure if we have that like listed or grouped on our website, but I'm sure if you search for that on the internet, just papers and scientific publications, you will find some of them. Not many of them, not some.
Controlling a whole satellite fleet from a couch is awesome, but does it bring additional security risks?
Yeah, of course. Our security team makes sure that there are all the security measures in place so that we can be able to do this. So it's not as easy as going to the website, for instance, but they make our systems easy to work with for us.
Cool. I think there's no more. Oh, no, yeah, there's no other question. So thanks again, Kattia. It was very interesting.
Thanks, Valentina. Thanks, everyone, for inviting me.